Here we go. Okay, so page 46, like I said, we're talking about galvanic or voltaic cells, which are just batteries, and then cell potential, which is like what's the volts that the batteries can produce. And then Gibbs free energy, like does it actually happen? Like if we put these two metals together, do we actually get a battery that works? Okay, so that's what we're looking at today. All right, these are redox reactions. Okay, so let's go over a couple of those big ideas from redox, like Leo the Lion says grr. Leo the Lion says grr. Okay. If we lose electrons, we oxidize. If we gain electrons, we reduce. And then we have a new one that will come up today, and it's red cat and ox. Okay? Red cat and ox. And the reason why is because in these batteries, you have cathodes and anodes. Okay? And red cat reduction happens at the cathode. Okay, so we got red cat. Okay, so reduction happens at the cathode, and then ox. Anodes is where oxidation occurs. Okay, so looking at this, first off, if something is in its elemental form and it does not have a charge with it, its oxidation number is 0. Okay? So zinc has an oxidation number of 0 on the reactant side, and copper has an oxidation number of 0 on the product side. Okay? If an atom is not combined with anything else, but it's an ion, then its charge is its oxidation number. So the oxidation number of copper here is +2, and the oxidation number of zinc is +2. Okay, so based on that, zinc went from 0 to +2. Okay, what does that mean? Losing electrons or gaining electrons? Losing electrons, so it oxidized. Okay, so zinc oxidized. That means that zinc oxidized. What is it, the cathode or the anode? Anode. Okay, so now copper went from +2 to 0. Okay, so is that gaining or losing electrons? Gaining, right? Gaining negative electrons. And so then that would be reduction, so it reduced. So copper is the metal, and this copper is the cathode. So it reduced, so it's the cathode. Okay. So we have these half reactions, okay? We have the zinc half reaction and then the copper half reaction. We said that, zinc oxidized and copper reduced. Okay, so zinc, we said oxidized and copper reduced. And if we combine those half reactions, then we get that full reaction, that overall that we were just looking at together. Okay. This is how these batteries work. So we have our, oxidation, so anox, so this is the anode. And then we have our metal, which is the cathode on this side. Okay. The other things that have to be present for the battery or the galvanic cell is we need a wire that connects these metals. Like we need something that electrons can travel through. Okay. And then we have something called a salt bridge. I'll explain what this is in a little more detail in just a moment, but it's where ions in solution can travel through. Okay, so here's how it works. At the anode, this solid zinc is going to turn into zinc aqueous. Okay, so this solid zinc is going to turn into zinc aqueous. Okay? And when it does that, it allows 2 of the electrons to now travel through the wire. So we have a little zinc atom that was solid, and then it loses 2 electrons that go through the wire, and it pops off into the solution and becomes zinc aqueous. Okay? The electrons travel through that wire, and then they go to the copper. And so you get this little copper atom here, and we are able to take copper that's in the solution, and it's going to attach onto and become a solid atom, because then the 2 electrons are given to it. Okay, so one more time. A little bit of solid zinc loses 2 electrons, and it pops off into solution. Okay, so boop. Kind of, yeah, you're right that the anode is eroding, or like it's getting smaller, okay? And so then those electrons travel over here, and then copper that's in the solution attaches on and becomes a solid copper, and it gains those 2 electrons. That's why it becomes copper without the charge.
So if we're like basically making the anode smaller, is that like when it's gone, is that when like the battery dies?
Yes, as long as we have a good salt bridge, okay? If the salt bridge isn't there, the battery only produces voltage for a very short amount of time, okay?
How does that like make energy?
Yeah, it's so movement of electrons. If we think about how the electricity works in this room, if I turn on the switch, it's not that an electron travels all the way through the wire and gets to the lights. What it is it causes all the electrons in the wires to shift and shift and shift. And it's that movement of those electrons that produces the electrical energy. Okay? And so we get the same thing. We get movements of electrons, and that's where we can get the battery. Exactly. Okay? So anodes will get smaller, cathodes will get bigger. We get to a point where they stop working, and it's usually when one of 2 things: either the metal is gone, or we've used up all the like copper ions in the solution. They've all attached on. Okay. The reason why we have the salt bridge is to keep the solutions as neutral. Because notice how this side is going to gain a whole bunch of positive charges in it. So in this salt bridge, let's say we had sodium sulfate inside the salt bridge, sulfate's going to come in here to start to neutralize this. Okay? Where on the other side, if we are losing copper positive items out of here, it's actually sodium, the Na, that's going to come down to neutralize. Okay? So the common misconception is that electrons travel through the salt bridge. This is not true. Ions do. Okay? Like the salt bridge allows for the positive things over here to move over here, and the negative things over here to move back over there. Okay?
So what would happen if we didn't have the salt bridge and it just became like a really positive solution?
Good. I believe that's when we have like a Q, we've made a Q value bigger than a K value, or, okay, trying to think of the best way to describe it. You know how when it was a common ion effect, how if the ion got too concentrated, it would make it go back to being a solid? Like, we're essentially stopping this reaction from happening. If we get too high of a concentration of positives here, it's going to stop putting positives into it. If we have too high of a concentration of negatives, because we were removing positives here, then it's going to stop taking positives out of it. Okay?
So basically be like saturated and when like...
Yeah. Exactly. It's
Nothing
like
being
it's
added.
saturated.
Okay.
Okay, cool. So, movement of electrons through the wire create the voltage. The reason why the electrons can move through the wire is because of the salt bridge, because ions can go between them. Okay, so that's how batteries work. Delta G is negative because this reaction is actually happening. Okay, like we're getting this movement of electrons. So if we have chosen appropriate metals, and even then, and we've put them in ionic solutions with a salt bridge that allows ions to travel back and forth, then we will have a negative delta G. So it's actually happening. When we get to a point that we have used up ions, or either we've run out of metal for the anode or we've run out of ions for the cathode, then delta G becomes positive. The reaction stops. Okay, cool. So this was our red cat anox. Okay. So when we reduce, that's when it's a cathode. When it oxidizes, that's when it's the anode. And this is what we drew earlier on the other page. Ooh, that's a good one. Because, well, the anode's the one that gets smaller, though. Dang it.
But like, reduce means like it's not.
Stops.
I know.
No, but I love the thought, right? We're on the right track there. Yeah, it starts bigger, right? Exactly. Yeah, good. Okay. So, let's write just a general one, because we have this, and that's helpful, but I know you're going to have to write these overall reactions, these net ionics, quite a bit. So, let's do just kind of this general idea of if you have a solid metal, and then you have an ion, aqueous, and then they're going to flip-flop. X is going to become the aqueous thing, and Y is going to be the solid. Okay, so X had an oxidation number of 0 to +1. So if we go from 0 to +1, gaining or losing electrons? Losing. Losing electrons is what? Okay, oxidation. So that means that this is, so we oxidize, and that's going to be an ox. So that's going to be the anode. Okay. And then Y is doing the opposite, so Y is reducing, and so that makes the metal the cathode. Okay? Questions on this? This is the net ionic for this, by the way. Okay? All right. Okay, I feel like we've talked through the next page. Feel good about that. Okay, on page 49, I just underlined one part because I think it's the most common misconception. Salt bridges are used to keep the solutions neutral, like we were saying. Okay? So the reaction can keep happening, exactly. These are super common ions that are found in salt bridges. And so we're not going to go into a lot of detail of like why these ones work better than others, but I did notice that there was questions saying like which salt bridge would be the best, and it had one of those things in it, and you go, that one. Okay.
So, like, what is a salt bridge, and like, how does it do that?
Okay, let's why is it called a salt first? Salt is ionic things, okay? And so it's got the ions in it, and it's a bridge because it allows it to travel from one side to the other. Okay.
Well, like, what is it?
So what it is, it depends on the battery, but for these really basic forms, it's a little tube that usually has gel in it, and it can allow those ions to travel through. Yeah. Because if we just had solution water, it would like fall down, right? Like it wouldn't be at a higher level than like the level of the solutions here. And so, yeah, no, exactly, it is. It's an ion jello. And so when we make it gel, then they're able to still travel through there.
We should make Jello at the end of the year and be like, and put different things in it and be like, look, it's our software.
We absolutely can make jello.
We should make Joe.
We should make
Okay,
batteries.
so I've seen multiple labs where they're like making a battery,
We should
okay?
turn on electric.
Maybe. What's fascinating, we're going to do calculations.
Well, no.
For some reason, like anything that we make voltaic cell wise in the lab is like nowhere close to what the calculated values are.
Oh.
Yeah, and I don't know why. Like we need to figure it out. But yeah.
So are we doing it? What? That's weird.
Well, it's across the board. You talk to any teacher, like these labs with voltaic cells, usually teachers don't do labs with them because, yeah, we can get a voltage, but then if you go and calculate it, it's like not close to what we calculated. It's lower than what we calculated. Yeah,
Is there a reason for that?
I'm sure. Now the question,
Maybe
do I
that's
know
not
the
rational.
reason? No. Yeah, figuring that out, right? Okay. Yes, thank you.
Like, have
Yeah, you got it.
people do
Okay.
different
We
things
had
to
some of
like,
those different,
like
levels of
different, or
solution.
like different amounts
Say that again?
of
We
solution.
both those solutions and I stuck my finger in both of them, like,
We'd also need a salt bridge.
yeah, there's a solver.
Then yes. Yeah.
If we do one, we should have different groups try different, like, amounts. So,
Yeah,
like,
different
one-
and different types of metals
Yeah,
to make a
and like
difference.
different sizes of salt bridges.
Oh, yeah, that's a good idea. And like find like the optimal.
Yeah, because it's like, maybe if we make the salt bridge bigger, then it'll get more. voltage,
Right,
and it'll go
exactly.
longer.
That's a good point. Good idea, guys. Well, I'll see if I can find a lab and we can put something together. Okay, so this is just a little bit of history that kind of ties with it. Milligan's oil drop experiment. So the scientist was trying to figure out what the charge of an electron was, because we had J.J. Thomson who discovered the electron, and then Milligan was trying to figure out what the charge of a single electron was. So he took oil and like vaporized it. Okay, so we have these little droplets of oil that would fall through, some of them would fall through this little hole here, and he would send X-rays at it, and the X-rays would kick electrons off of it. Okay?
Was he just sitting up and was like, what if I just like vaporize
I-
oil?
right.
Put an X-ray down.
Exactly, I don't know.
Explode this oil and like see it.
So now here's the cool part. These two plates are charged. Okay?
One of them is negative.
Yeah, exactly. And so what is, and actually I think these are flip-flopped.
And then would the electrons get,
Because if we kicked off the electrons from the oil, it actually makes it positive. And so then it's attracted to the negative plate and repelled from the positive plate. And so if this is the positive plate and this is the negative plate, if you got the right amount of electrons to be ejected from it, you could actually get the oil drop to float.
that's cool.
Yeah, that's what the little microscope was looking at this to see at what point will it float or slow down as it falls. And so based on those ratios, he was able to find the charge of the electron.
That's fun.
Yeah, isn't that cool?
Kind of hurts my brain.
I agree. So, their volts, okay. Volts are joules per coulomb, or charge of electrons, okay? Like coulomb charge. So, often we just use, for volts, we use units of V for volts. And then other times I've seen it, and I'll show you which equation, where it's joules per coulomb. Okay? All right. We are not using this equation. I just wanted to point out units on it. Okay. All right. We are going to jump to calculation. So turn to page 51. Okay. Reduction, because we have Leo the lion says grr. So gaining electrons is reducing, right? And so all of these are reduction half reactions, where we have something that is gaining electrons. And then we see what the cell, or not the cell, what the potential, the electrical potential, or cell potential, is measured in volts for that half reaction. Okay?
Maybe, I just had a thought. So in that battery lab, maybe it's like, I just had a really good analogy. It was like how the potential is something, but it's really hard to get there, so we don't always get there, like, because we can.
Yeah, right. It's kind of like a theoretical versus an actual yield, right? Like, theoretically, this is what we should be at. But actually, it was this. Okay, so everyone, I am going to show you and tell you the super easy, fast way of doing this. Okay? Then I'm going to walk you through more of like the detailed of why it works and how it happens. So, to calculate the potential or the voltage of a battery, E cell, like a battery cell, okay? We want this to be as big as it can be, and we want it to be positive, okay? Positive means that we're getting positive voltage, like we're at the battery's working, okay? So your goal is for this to be positive, and it's going to be the E of one metal minus the E of another metal, okay? It's going to be the voltage of one metal minus the voltage of another metal. One's the cathode, one's the anode, okay? The reduction, so the item that's actually going to be reducing, that's the red cat, so cathode. That's the one that goes first. And then minus the reduction reaction of the anode. So it's actually the one that oxidizes, but it's happening at the anode, anox. Okay. I don't focus in on like, oh, I always minus from the anode. Instead, what I'm doing is I'm saying, what makes this the biggest number? Okay, the biggest positive number. So what if we have these two right here, and what if I don't tell you the cathode and the anode? Okay, I don't give you that. Which number do I want to go right here? Do I want the 0.342 volts or the negative 0.76? The first one, exactly. Okay, so I want this one to go right here. And then where this is a negative number, it's going to be minus that negative number. And so I want that one to go right there. Okay.
I know I'm going to sound like Jacob, but how do you have a negative voltage?
It's a great question. How do I describe? Let me think. Okay. It's less of a negative voltage. It's more of if you take the inverse of this reaction, then we have a positive voltage. Right? Yeah, I mean, like, it's not that we measured a negative voltage. It's that we weren't getting a voltage until we took the inverse of it, and then it was a positive amount of that. Okay?
So is the E cell always going to, do you always want that to be a positive number for the battery to work?
Exactly. The bigger positive number, the better. okay? If it's negative, then it's not working, then it's not conducting.
So is the negative voltage just like, from that reaction, we're losing voltage instead of like,
Yeah, from that reaction, it's preventing this amount of voltage,
okay.
okay?
It's not like, and like a negative amount, it's what we're losing.
I think that's a good way of thinking about it, but it's never truly in the lab gonna be zero, or sorry, less than zero, I mean. It can be zero, we can have zero voltage, it's not happening, but we're not gonna actually have a negative voltage.
Like in the other like stuff that we've done, like with heat,
Mhm.
it's what we've lost, not what it is.
Yeah, exactly. So here it's like, what is it preventing voltage from traveling? And if it's big enough, then it's going to just make it zero instead of forcing it into then the negative range.
So technically, does the second equation have a higher voltage because voltage is really what positive?
Exactly. If we take the inverse of that, and instead of zinc gaining electrons, we have the zinc solid losing electrons, that produces a higher
Then we
voltage.
don't have, then what we have to do, the inverse of the copper, and then
And then we don't want to do the inverse of this copper because it's already positive.
no, like if we flip the zinc,
Mm-hmm.
would we also have to flip the copper?
Oh, no, good question. No, we wouldn't. And let me show you why. So if we combine these just in the way that you guys are saying, so what if I leave copper the way it is, because this is a positive, so it's going to be copper 2 plus 2 electrons turns into copper solid, and that gives me an E value of 0.342. And then I'm going to take the inverse of this one, so it's going to be zinc solid turns into zinc 2 plus 2 electrons, and then we take the positive of that, so 0.762 volts. Yeah, it's the half reactions, exactly. It's the oxidation and it's a reduction half reactions. So if we put these together, the 2 electrons cancel, right, reactants products, and we get copper 2 plus zinc solid turns into copper solid and zinc 2 plus. And then we just add those E's together, and that will be the E cell, and it's the same thing that we got before.
So why do we take the positive of the second equation?
Let me explain why. Let me get this number really quick. So I'm doing a 0.342 plus a 0.762, and then I get digits after the decimal, because I'm adding them together, 3 digits after the decimal, 3 digits after the decimal, so 1.104 volts for this cell, okay? And that's the exact same number as what we got before when we did this one minus the negative of that one, okay? Now, back to Kale's question, why not just do it this way and take the inverse of it? You absolutely can. You're usually given reduction half reactions, not oxidation half reactions. Like usually, they give you the whole list of these and they're just reduction ones. And so if you don't want to have to like worry about remembering to flip it, then you just need the minus, okay?
If you put the negative in, it just flips it because 2 negatives make a positive, so just 2.
Well, and it's just like we've talked about before. If we have a reaction and we take the inverse of it, the delta H's became positive or negative, the opposite, and it's the same thing for E potentials here, okay? So the bigger the E, the voltage, the greater capacity for reduction, okay? That we want this cell to be the biggest number possible, okay? So you're reducing things, the cathode, red cat, okay? So you want the cathode to be the biggest positive and you would want the anode, sorry, the biggest positive, you would want the anode to be the biggest negative, because we know we're going to take the opposite of it or minus it. Okay. Okay. Everyone, I want you to write these two down because you're going to need them for the problem set. Okay, so in addition to that list that you have there, you also are going to need CD2 plus 2 electrons, gives you the solid, and there's the E for it. It's a negative 0.40. And there's gold. If you can't read any of that, yell at me and I'll talk to you. Briggy, you're going to need these for the problem set.
Or what's the number for the first one?
For this one, negative 0.40 volts. Okay, the other one that's not on the list that you use quite a bit is the lead one. And lead, you'll see it on the next page. Oh, no, sorry, on page 53. It's there on page 53. So just a heads up that, like, that's one other on the problem set you will need that's not directly in this list here. Okay?
So will these like reactions always be a reduction reaction with a positive and one with a negative?
No. And so then you just have to think through what gives me the biggest positive E cell. Okay? So, like, let's say that, see the one that's 0 and all the negatives? Let's pretend none of those metals are available to us. Okay? If none of those metals are available to us, I'm going to choose silver to be my reduction, so my cathode. And then what one do I want for my anode? Yeah, exactly. Because it makes the least negative impact on it, right? Like, even though it's going to be minus 0.34, because we're going to minus it from that, it gives us the largest E cell in the end. Okay?
So the best ones would be the top one and the bottom one to use.
Exactly. Those would be the best. Exactly. Okay. So, number one, you decide which method you want to use. You can either use the long method, that's what I did here, where I took like the inverse of this and then I added them together, or you can do that like minusing one. All right? So give number one a go.
Do we need to write out like the equations before
No, only if it asks for it. Okay. Okay, all of these E values, by the way, I forgot to mention, see how they have the degree symbol with them? 25 degrees Celsius and 1 molar concentration, okay? 1 molar is like our standard concentration.
Do we have to write little degrees when we find our
No, you'll be okay. But on the problem set, it's like, what's the concentration need to be? 1 molar, okay? Because that's the numbers that we got from this are for 1 molar solutions, okay? All right, so I notice I want my E cell to be the biggest, so I put the positive number minus the negative number. Remember, the first item is your cathode if it asks you what one's the cathode. And so then you can say, oh, the cathode is going to be the copper, and the anode is going to be the nickel on this one, if it were to ask for that. and I got 0.59 volts. You guys get the same? Okay, awesome. All right. Look at number 3. Number 3, it tells us in a galvanic cell, aqueous silver is reduced. Okay, so this is important information because if we're doing this E cell and it's reduction minus reduction, right? These list of reducing half reactions, okay? Like these lists where they're all reduction because we're gaining electrons, right? It is the cathode minus the anode, okay? So the cathode minus the anode. And so we know red, cat, and ox. So if the silver is reducing, then it's the cathode. Okay? So the 0.80 is going to be the cathode. And we are told that the cell potential, so this E, is equal to 0.47.
Wait. Why is it the cathode?
Because it reduced. Silver is reduced. Red cat, reduced cathode. Okay? And so that's why this is the 0.80 volts. And then it tells us that the cell is 0.47 volts. Okay? And it's like, what's this? What's it going to be for the anode? Okay? So go ahead, give that a go, rearrange as needed, and then we will solve for that. All right. So if I'm solving for this negative, I added it to the other side. So there's my E for the anode, and then I subtracted the cell. Okay, so that means I took 0.8 minus the 0.47, and so the potential for the anode was 0.33 volts. Okay. Beautiful. All right. We are doing awesome. Do we need a brain break? You need. Then you want to do the number one? Okay. All right. Let me turn the lights on. Okay. So, should we do 1 through 100 or small? 1 through 100. All right. Write down a number 1 through 100.
Are you randomly generating it?
Yep.
Okay, so there's not going to be bias involved.
This is without me clicking it. Yeah, so it's not 3. Okay, so. All right, do you guys all have a number?
Wrote it down.
All right. 90.
I have 77.
Anyone higher than 77?
Oh, I have 82. Whoops.
Girl,
I don't know.
Either way.
There's so
you
many
beat
numbers
yourself.
on my page.
All right, Elizabeth. 1 through 24.
72.
Wait, I actually had 90.
3.
3, okay.
Pin or sticker?
Oh, it's another swimming and there's a little ducky on it. Oh, no. Okay. Either keep your number or change your number. Okay.
Good feeling.
Keep your number, change your number. All right, here we go. Ooh, 85.
Changed it.
I should have changed that.
82. Okay, who's our next one?
I have 66.
Anyone higher than 66? 68? Anyone higher than 68? Okay, nice. Yeah, 1 through 24 to make it. And then 1 through 9. 7, this one's in here as well. Oh, it's a kitty, and it's his birthday, and it was happy birthday,
I want to
guys.
get earrings.
Okay, let's do one more. Okay, so either keep your number or change your number. Keep it or change it. I would be the same way. I would never change it. Okay, here we go. Ooh, 79.
I should have kept it.
Okay, who
75,
who has a number higher than 50? Okay, Briggy, what was yours?
52.
Okay, let's do that. Briggy 1 through 24.
Kept it.
17.
I don't think these numbers are random enough.
Oh, and
Good one.
Slug.
which one is there?
You got a slug last
I
time.
need more slug. I want to
I need more slush.
Yeah. I have my one squeaky slug and it's by my bed.
Oh,
It's so cute. This one actually really does get a Briggy.
oh, there's no way.
Wait,
Yo!
That's awesome.
that's
Really
sweet, but
creepy, but-
horrifying at the same time. That's a little
You're gonna like unleash it on the
Potential.
period.
What's
Yeah.
the potential voltage?
Yeah, we should put some battery voltage in it. Battery
You should,
point of-
did you,
I know.
you should show the recording now. It's so cute.
Okay.
Oh, it's Friday.
Yep, Friday.
Oh,
I love like forgetting and then remembering. It's Friday.
Okay, everyone. So, bottom of page 53. Okay, this equation is in your reference guide. So let me tell you what each of these items are. So it's Gibbs free energy again. So we're looking for a negative delta G minus N, and N usually is reserved for moles. And in this situation, the moles is the moles of electrons. Okay? So like look back at this one. Do you see how 2 electrons are gained and 2 electrons are lost? That means it would be 2 moles of electrons. Okay, it's like the coefficient in front. Okay, then F is a constant, and let's update it. So on your reference, okay, let's find it. No, there's like,
Yeah, what if that came crawling up to you at like 2 a.m.
It's the next
I'm gonna be keeping my backpack out of my room.
okay, so everyone, its placement is a little funny. It's right here. Okay, so everyone, 96,485 coulombs per mole. Okay, so coulombs per mole. Faraday's. Farquaad's, yes, yes. Farquaad's constant.
That's how you know you made it as a really short king. You have your own
Constant, yeah, I agree.
I wish I had my own.
Okay,
Constantly short.
so let's update this. So F is going to be 96,485 coulombs per mole.
That's a lot. That's a lot of F to get.
That is a lot.
I don't get that many Fs.
The recording.
Yes, it is recording.
I hope,
gonna be fun.
I hope they have such a fun time.
Oh, yes,
And you can
absolutely.
just hear the sound of Ricky Slug in the background.
Yes, exactly, and Briggy Slug crawling around, it's great.
Hey, it's keeping him awake.
This is what I like your nail.
Thank you, me too. So I did the holographic glitter because I wanted to see if during the eclipse, if it would look different.
Oh.
It didn't, but that's why I chose it.
though.
Yeah, thank you. So we have reminder, this E potential is volts, and volts is the same as joules per coulomb, okay? All right, so we're gonna use this equation. Oh, and then we're just E cell, like we've been calculating, okay? All right. Moles of electrons. Okay, so example number 4. Okay, something interesting. Do you see how we have 3 electrons and then 2 electrons? And we need them to be the same. Like we need to be gaining and losing the same amount. And so I just multiplied everything here by 2 and everything here by 3. But what is crazy is you do not multiply the E values.
Really?
Yeah, I looked it up this morning, like just to double check, because I was like, no, there's no way. Yeah, we don't. It does not impact this. I agree.
I feel like there's a way to explain this. I feel
Okay,
like it makes
I'm ready.
sense, but I don't know how to explain
But like everything in math is taught me to like multiply that as well.
I know. So,
Why is chemistry so hard?
Maybe, oh, wait, so maybe it's like, so you can multiply them to be bigger, but in the end, when you reduce them,
mhm.
like, if you were to reduce them as a fraction, it would just come down to that same number.
Yeah, maybe that's a good idea. What I want to remind you guys, though, is if it was a delta H, we would multiply it, okay? And if it was a K value, we would raise it to that amount. All right? All right. So if it's an E, you don't do anything, surprisingly. Okay, so if I want this to be as big as it can be, then oh, and they're both negative. So wait, why did I choose 0.74 to go first then?
That's the most positive.
Yeah, exactly. Of the two options, it's the yeah, it's closest to positive, right? And then I did minus the negative, and so then plus the 1.18 volts, and that gave me with 0.44 volts. So that's my E cell. Okay.
it. Well, most of the time, we should get a positive number, right? Or all the time.
I want to say all the time, right? Like, if you got a negative, then you'd be like, this battery's not working. Like, delta G would be negative, or would be positive. This reaction's not happening. The battery's not working. Exactly. And then just don't forget, because again, not on this problem, but on another one, it could ask you what's the cathode and what's the anode, and it's always going to be cathode minus anode. So cathode minus anode. So chromium is our cathode, and not magnesium, manganese is our
Mac and cheese?
manganese. Manganese mac and cheese is our anode. Okay. So
Mac and cheese? I'm really out of pocket.
the element mac and cheese, yes.
Yeah, it's just milk, butter, and water.
She's got a lot of F's to give. for mac and cheese.
I have no F's to give as long as I have lots of mac and cheese.
Okay.
Alright, can we move on?
Anyway,
I'm looking like a little bit ahead, and so will G always be negative because of the negative?
Yes, exactly.
As well as-
Uh-huh. If the battery doesn't work, right, then it would be a positive G, because this would be a negative, right?
All right, yeah.
Okay, so
You know, if you-
here's the reaction. So we got delta G is equal to negative moles of the electrons, that Faraday's constant, and then the E cell. So we ended up multiplying this, so it's 6 moles of electrons. Okay, so 6 moles of electrons. There's the constant, and there's my volts. And I just changed the units. You don't have to. I'm just pointing out that coulombs cancel and moles cancel, and that's why you're left with joules for Gibbs free energy.
Wait. How many moles are there?
6. Because here it said 3 electrons and 2 electrons, and I needed them to be the same. So I multiplied everything by 3 and everything by 2. Okay. Okay. The bell's about to ring. The good news is the electrolysis, this thing, is no longer on the AP exam, so we got through what we needed to. Good job. I put the items up there that we're skipping. So on page 25, number 2E, we're going to skip, okay? Yeah, number 2E, right away we can say this is the right answer because it has the nitrate in there, but you don't need to explain. And then 3, 6A, 6E, and 7 in its entirety, okay? Answer key is up here, so feel free to take pictures of that. Okay, I'm gonna have an awesome, thing planned for us, so get this problem set done. You can do it.